Okay, so now for this video, we're going to attempt to solve an FE type question covering an ideal Rankine cycle. So for this video, I'm going to try to give you an overall picture of the Rankine cycle so you can solve other FE type questions, not just this specific question. So we know here that we have a graph that's given below and shows the Rankine cycle. So they tell us it's a Rankine cycle using the pressure versus enthalpy diagram. So we have pressure on the y, enthalpy on the x. The pressure at stage 3 is 1.0021 megapascal. So we know, let me denote this, the pressure at this point, state 3, so P3 is 1.0021 megapascals. And the pressure at state 4 is a 101.35 kilopascals. So the pressure at 4 is 101.35 kilopascals. The enthalpy in kilojoules per kilogram, we want to find the enthalpy at state 4 is most nearly what? So what we want to find is the enthalpy. So we want to find our enthalpy at 4, right? At state 4 being here. So what do we do here? We know we have an ideal Rankine cycle. So let's quickly draw what's happening in terms of the systems we have in the Rankine cycle. We know we're going to have a pump, a boiler, a turbine, and a condenser. So we start, let's say we're going from the condenser to the pump. So I'll draw my condenser first. This is the condenser. And we know we will go to a pump here. And we will have our pump that looks something like this. And the pump is going to have a work input, right? We want to input work into the pump to make it operate. So we need to provide some work. So it's work in. And we know what's leaving this condenser. We'll call it 1. This is the first stage. And it will be essentially on the figure that we're given using the pH diagram, it's going to be from 1 to 2, right? So we're starting at 1. So this is what enters the pump at 1. So we know this is at this line, which is going to be on our dome. It's the saturated liquid line, right? So anything to the left of the saturated liquid line here is going to be a liquid, right? So we're right at that point of saturated liquid. So saturated liquid is going to enter the pump. And I'll denote this as P for pump. So after the pump, we leave, we release some fluid, right? And this is going to be the liquid. So we're releasing the liquid, we'll call it 2, and we enter a boiler. And this boiler, we know we're going to have to add Q in. So we're adding heat because it's a boiler, right? We're trying to boil the fluid that comes in, the water, the liquid, essentially. So where's this at? So what we did was come into the pump here. So we went from 1 to 2 and we came into the pump. Notice we're in this region now because we're in this line. This is completely liquid. Anything, this is the saturated liquid line, right? Using the vapor dome. Anything to the left of this is going to be a liquid here. So we are coming out as a liquid. What enters the boiler will be a liquid, right? Then the boiler serves the job of boiling the liquid into steam. So then from the boiler, we exit. We come down and we go to a turbine. And we'll call this 3, and we enter the turbine at 0.3 here. So at the boiler, we know we're at a constant pressure, but we're increasing in the enthalpy. So we're increasing in enthalpy and increasing the temperature, right? We're adding heat. So we're at a constant pressure, increase in temperature, which increases the enthalpy, and we're coming into the turbine at this point. This point, notice this is important. We're at this line here, right? We're touching this line on the vapor dome. This is our saturated vapor line. So we're at saturated vapor, right? we're essentially at a gas stage, right? At that gas phase. So we've just become steam. And anything to the right of this is going to be superheated. So it's going to be completely vapor. So we're superheated to the right. This is the saturated vapor line. And we're at the saturated point at 3. Right when we enter the turbine, we're saturated vapor. So after that, we come out and we go down and we end at 4, right? We come back to the condenser. So we come down to 4, and at 4 we're in a mixed state. So what's happening here, we know we're in a mixed state in this region, in the vapor dome. So just to clarify, I want to draw the vapor dome, because if you do not understand what we mean by a vapor dome, I want to just cover everything as a whole in this example to avoid doing any more Rankine stuff. So this is the critical point. So what I'm doing again, I'm just drawing this dome, right? This dome here, which you have to have a good understanding of if you want to be successful in these questions. So this is going to be what line? This is saturated liquid. Saturated liquid. So that's a saturated liquid line, meaning anything to the left of this line is going to be just a liquid. So we have a liquid to the left. So now the saturated vapor line is going to be this, right? This line. So this is saturated vapor. And anything to the right of this is going to be what? Just superheated region. So we have steam or superheated vapor. And what else? We know in between we are in the mixed state. So here, think about it. What do we have? We're going to have saturated liquid. No, sorry. We're going to have liquid and vapor. So it's a saturated liquid and vapor region. So we're mixed. So we have saturated liquid and saturated vapor. And we know the top is the critical point, and we know this is temperature versus the specific volume. So temperature versus the volume. So we have to understand this, and this is going to be the compressed region. This is going to be the superheated region, right? Everything to the right here of the saturated vapor line is superheated. Everything to the left here is compressed because it's a liquid. The liquid is a compressible fluid, right? So it's going to be the compressed region on that left. It's just liquid, just water. So now, based on that, you have to understand that when you're doing these questions, right? When you're looking at cycles, any cycle, the auto, Carnot. So we have to know this dome, right? Our vapor dome. So now we've talked about this. We've talked about what's happening here. And going back to the original question, we want to solve for the enthalpy at state 4. So what's the enthalpy at 4 here? And before we proceed to that, we know that from 1 to 2, what kind of process do I have? We know it will be reversible. So it will be adiabatic isentropic compression in the pump from 1 to 2. So let me write that here. From 1 to 2. So you will have reversible adiabatic and it's going to be isentropic, meaning what's isentropic? It's constant entropy, and that's from 1 to 2. This is compression in the pump. So now from 2 to 3, what do we have? So I'm looking from 2, well, essentially for this point, 2 to 3, you're going to have constant pressure, heat addition in the boiler. So we're just adding heat. And it's at a constant pressure, right? So Qn for that. Then from 3 to 4, it's reversible. And it's going to be adiabatic as well, meaning no heat transfer. And it's still isentropic. and this is expansion through the turbine. So this is gonna be compression for the pump, this is expansion. So reversible, adiabatic, and it's still isentropic, meaning no heat transfer. So we know it's isentropic because it's a reversible, internally reversible process. So you have to remember that internally reversible means you have isentropic, you have no change in entropy. So that's important as well, and this is going to be 3 to 4 will be expansion. I'll just write exp, expansion. Then from 4 to 1, it's going to be constant pressure still. So we're at constant pressure, right? From 4 to 1. This is the pressure. We do not change. And this will be the heat rejection in the condenser. So I didn't denote it here, so we're losing here. So Q out, we're rejecting heat to the environment. So this is Q out. At what? A constant pressure, we have heat rejection in the condenser specifically. So that's the overall picture here, and why I did that, because I'm looking where we know we're given the state at 3, right? We know we're given this. And at 4 is what we want to determine, the enthalpy at 4. So we know we need to somehow find this enthalpy, but we know at 4 we are in a mixed state. So anytime you are in the mixed region is this, right? Using our vapor dome, it's this region. So we are in this region at 4. Anytime you're in the mixed region, you're going to have to find that quality. We always need that quality value. So that quality value, if you refer to the handbook, we can look at the thermodynamics section. We're going to use these equations. So we need to find that quality because we're in the mixed region, and this will help us determine our enthalpy, which is H. It depends on H sub F. So here we know it's going to be, the F is going to stand for the saturated liquid, so the enthalpy at the saturated liquid, and Fg is going to be the change in vaporization. So it's the gas minus the saturated liquid. So we need to find this H, which is for state 4, and we know this depends on the quality. But we have to also think about what's happening from 3 to 4. If you go back from 3 to 4, we know we have constant S value. The S value, which is the entropy, is going to be 0. So the S at 3 is going to equal to the S at 4. Because we said from 3 to 4, it's reversible and adiabatic, and it's isentropic. It's isentropic when we're going through this turbine from 3 to 4. So we have our delta S is going to equal to 0. We have no change in entropy. So from 3 to 4, we know that S3 equals S4. So this will help us determine the X value when we relate it to the entropy from 3. But first we need to find the entropy at 3, right? So we need to find the entropy at 3, and the way we will do that, we're given a pressure. So we know we are also at a saturated liquid state because we're touching this line. Sorry, with a saturated vapor, this line is vapor. We're touching the line here at 3. So we can use the steam table and extract the value for S3 at this pressure. So if I go back in my steam table, we're at pressure 1.0021. So let me go back to the thermal, do Control F, type in steam, and Control F, steam. You can go down, and we're at 1001, and it should be somewhere this one. So we're at this pressure, and we go all the way to the right. I want to extract the S value, which is going to be for saturated vapor, right? We're hitting that line at saturated vapor. So you go to the right here, all the way here, and you get this value. So it's going to be around 6.5857, and the units are what? Kilojoules per kilogram times Kelvin. So let me go back. So let's write that down. S3, which equals S4. The entropy at those are the same. And we have a value of 6.5857 kilojoules per kilogram Kelvin. So we have that now, and after that we can find the quality. Again, the end goal here is to find the quality, to find the enthalpy here. We need to find the quality because we are in the mixed state at 4. We need to find that X value. So to find that quality, we will use this equation. And it's going to relate the entropy. So we will use this equation. We know the entropy at 4, right? This we found from 3. They're the same. This S sub S we can find. We can solve for X, which is what we want. And this we can also find from the steam table. So let's go back, and if I do that, we know that the S4 is going to equal S sub F plus X times S FG. So we are solving for X, rearrange the equation, solve for X, which is what we want, that quality at state 4. And do SFG. S4 is going to be this value, right? So I just put it in here. SF and SFG, we have to use the steam tables again, but be careful here. Don't make this mistake of using this pressure, right? We are given the pressure here. We're given the pressure to be 101.35 kilopascals. So we have to look at pressure 4, right? So we have to look at this pressure to find this and this. So using the steam tables, we will do steam tables here, and we are 101 kilopascals, which is gonna be approximately 0.10135 megapascals. So we're at this pressure. You go all the way to the right, and you want to extract the saturated liquid and the evaporation. So the difference between the saturated vapor and saturated liquid. So this is the saturated liquid, which is S sub F. This is gonna be the difference, which is the evap, and we can plug those in the equation. So let me go back. S4 we found, it's this 6.5857 kilojoules per kilogram Kelvin, minus S sub F is gonna be 1.3069 kilojoules per kilogram Kelvin, divided by the value at the bottom from the steam table, kilojoules kilogram Kelvin. And now we can solve for the quality. You should get 0.873. So we know this is what's leaving the turbine. So this is, we know we have around 80% vapor leaving the turbine. So after that, we can finally solve for H4. Again, we have the quality now, and we needed that quality to solve for H4 using what equation? Using this equation now. H4 is going to equal to HF, so the enthalpy for the liquid, saturated liquid. X is the quality we have, and this is the difference between the saturated vapor and liquid. For the enthalpies now, we're looking at enthalpy. So let's solve for that. H4 is going to equal to H sub F plus X H sub FG, and we H sub F we need to get from the steam tables, right? So H sub F at state 4, right? So at this pressure of 101.35. So we need to get that. So if you do Control F, steam. So HF is going to be this saturated liquid. So it's going to be around 419.04. And we need also at the same time, let's get the evap. And we extract that too. So we need these two to use that equation, right? So H4, the enthalpy at 4, is going to equal to HF, which is going to be the 419.04 kilojoules per kilogram. Again, I got this from the steam tables at a pressure of 0.101 at the, as we denote it for the pressure at 4. Then we multiply by X, which is the quality, which is 0.873. Keep it in decimal form. And HFG we found is from the steam tables is 2257.0 kilojoules per kilogram. So the units look good, right? We can, at the end, we will have that kilojoules per kilogram, which is what we want in the question. So you should get the enthalpy at 4. It's going to be 389.4 kilojoules per kilogram. So this should be our answer here. And it should be, I believe, B. So that's all for this one, but before we finish off, you can pause or just skip the video. I just want to tell you that for the pump, we can find the work for the pump. I'll give you these general equations. We know from 1 to 2, we're going through the pump. And we can find the work in that we have to supply to the pump is going to be the change in enthalpy from 2 and 1. So it's the difference. We're looking at the pump. We're isolating the pump, right? And we know at 2 we come out, at 1 we come in. And we just take the change in enthalpy. We're doing conservation here. Or you can take the pressure times volume. So it's the change in pressure essentially, which is the pressure at 2 minus the pressure at 1 times the volume. This applies as well if you have the pressures. This is for the pump. So now from the 2 to 3 we have the boiler. And for the boiler, we know the work is going to be equal to 0 because it's adiabatic. So for the boiler, it's adiabatic. Oh, I'm sorry, it's not adiabatic means the heat, there's no heat transfer. For the boiler, we have 0 work, right? Obviously, the turbine, I didn't denote this here. The turbine, we have work out, right? That's the whole purpose of the turbine, to release work that we will use. So for the boiler, we have no work, so the work is 0. And we know that Qn, the heat we supply, is going to be the change in enthalpy. You're just doing conservation. And now from 3 to 4, turbine, we know Q equals 0. It's adiabatic. And we know the work out is going to equal to the change in enthalpy. So what's happening here is you're essentially applying the first law of thermal to each system, but this is like the final steps for each system simplified. So you just have to know these. If you're given any FE type question, you'll be able to solve these for a Rankine cycle. And for a condenser, the work is going to equal to 0. And we know that Q out, the heat rejected, is going to be equal H4 minus H1. Again, it's H4 minus H1 because I'm only looking at the condenser here. And you do the difference in enthalpy for the condenser. So I think they'll be all these will be helpful equations, so you can have them on your equation sheet when you're looking at the Rankine cycle. And this will also help you understand other cycles as well. So let me know if you have questions. Don't forget to subscribe and like. Take care.